Welcome to this lecture. Before we continue the discussion about the topics in this lecture, let's quickly recall what we have done in the previous lecture. So in the previous lecture, I looked at the random variables or random vectors defined on a probability space, and then what we considered was the measurable structure of such functions, and we combined it with the probability measure on the domain side to construct a probability measure on the range side. So for random variables, the range will be the measurable space real line together with the Borel sigma field. For random vectors, if they are taking values in Rd, then the range side will be Rd together with the Borel sigma field of Rd. So on such range spaces, range side measurable spaces, we constructed these probability measures that was combined together with the measurable structure of x, the random variables or random vectors, together with the probability measure p, and we called it p compose x inverse. The notation was p compose x inverse, and we called it the law or distribution of the random vector or random variable x. So we constructed this and we saw one simple example given by the Dirac mass, and then we left as exercise some of the other related examples. Okay, so please compute the laws and check how they come out as combinations of Dirac masses. So those exercises will give you examples of convex linear combinations of Dirac masses. Okay, so in this lecture we are now going to continue discussions about the probability measure that we obtained, and we are going to construct a very important function out of this. Again, as seen in the previous lecture, many of the probability of the events that we considered in your basic probability courses can now be reinterpreted as probability measure of the corresponding set that is appearing on the Borel sigma field or the real line or the RT, right? So a similar thing is going to happen here. We are going to consider a very important function that you have seen in your basic probability course, and we are going to obtain it from this specific probability measure, the law or distribution of the random variable or random vector x, the probability measure which is p compose x inverse. So let's continue and move on to the slides. So in the previous lecture we have defined the law or distribution p compose x inverse of the random variables or random vectors x, right? And they are supposed to be defined on some given probability space omega fp. And as per the definition, p compose x inverse became a probability measure on this space. Okay, so if you are considering this Rd valued random vector, then you just get Rd, b of Rd, that's measurable space. So on top of that you get this probability measure, and now we are going to define something called the distribution function of a probability measure. So this is a general definition of a function corresponding to a probability measure on Rd or R. Okay, so either of these spaces. So let's first look at dimension 1 just to understand the concept. So start with the measurable space Borel sigma field on top of the real line, so that's the measurable space, and consider mu to be a probability measure on there. Okay, so now consider this function f subscript mu defined on the real line and taking values between 0 and 1. So what is this function? This function for any real number x takes the size of the set minus infinity open to closed small x. So that interval you look at, minus infinity to x, x closed, so that interval you look at the size of that under the probability measure mu, and consider that as the value of the function at the point small x. Okay, and this is called the distribution function of the probability measure mu. Okay, and for the d-dimensional case you have the exact analog of the same definition. So now you are defining the function on Rd, and it will again take values between 0 and 1. What you have to do? Look at a point x in Rd. So it's a vector with components x1 up to xd, and for such a point small x, such a vector in Rd, what you look at is this rectangle. So the ith coordinate is simply this interval minus infinity to xi. So it's a product of such intervals. Okay, so it's the default product of intervals of this type, where the ith component is simply coming from the ith coordinate of point small x. Okay, so you get this rectangle, and this is a set in Rd. This is a Borel set in Rd, and therefore you can talk about the measure of that under the probability measure mu, and then you get a value, and that value you assign it to this function at the point small x, and this is called the distribution function of mu in the d-dimensional setup. So exact analog of whatever you have seen in the dimension 1, right? Alright, but then with that as the motivation, you can now define distribution function of random variables or random vectors. Okay, so what do? Take a random variable or a random vector defined on a probability space omega fp. Correspondingly, you get this law which is p compose x inverse, and that is defined on BR for the case of random variables. For RD valued random vectors, you get it on RD with the Poodle sigma field of RD. Now, corresponding to that probability measure, you get a distribution function as defined above, right? Consider that. So that's nothing but, as per our notation, f subscript p compose x inverse. This function is called the distribution function of x. Okay. So again, for a random variable or a random vector, you get the law, which is the probability measure on the range side, and on the range side you have defined, for any probability measure you have defined this distribution function. Take that. So call that as the distribution function of x. Okay. And now, to simplify the notation, what we are going to do is to forget about this probability measure now. So it will be given to us, but we will simplify the notation, and instead of writing f subscript p compose x inverse, we will simply write f subscript x. So this is the distribution function of x. Alright. But then follow the notations mentioned in the previous lecture, and let's rewrite this the distribution function of x. Let's try to connect it with probability of events. What is this? So if x is a random variable, so you are working in dimension 1, you get back some nice familiar expressions. So for any point x in the real line, so as defined above, if x evaluated at the point small x is nothing but the f subscript p compose x inverse evaluated at the point small x. So this is just a notation, but then as per the definition, this is p compose x inverse of the interval minus infinity to x. So you are looking at the size of the set, size of the interval minus infinity to closed x under the probability measure p compose x inverse. And as per the notation introduced in the previous lecture, this is nothing but the probability of the event capital X less equal to small x. And therefore you get back your familiar distribution function corresponding to a random variable. Okay. So this simply turns out from the definition of the law. Okay. Alright. And similar expressions can be derived for the random vector case. So again, if you are working in d dimensions, take a point small x which is made up of these components x1 up to xd. This is a vector in RD. So try to compute the distribution function at the point small x. So that is nothing but, as per the definition, p compose x inverse of this d-fold product of the intervals, right? So you are looking at this d-fold product of the intervals and looking at the probability measure of that. So under the measure p compose x inverse. But then what you are saying is that you are looking at all points in the domain small omega such that the random vector evaluated at the point small omega, that is nothing but x1 small omega comma x2 small omega up to x subscript d small omega. So that's the d components. So that thing should land up in this d-fold product, and therefore what you are saying is that you are looking at all points on the domain side such that individual components xi evaluated at small omega exactly falls in these intervals minus infinity to small xi. And that can now be rewritten in terms of xi evaluated at small omega less equals to small xi. This is simple inequalities you can write down, but this should happen for all the coordinates I from 1 to d, right? But then you can now rewrite using your familiar notation, suppress the small omega and simply rewrite it in terms of probability of the first coordinate less equals to small x1, second coordinate less equal to small x2, the dth coordinate less equals to small xd. And that's nothing but the distribution function of the random vector x. Again, you are getting back the familiar expression. Now we go ahead and look at certain simple examples to understand these computations of distribution functions. Okay. So in the previous lecture, we computed the law for this constant or degenerate random variable, which was taking value some constant, given constant value, and the law was exactly the Dirac measure situated or supported at that point, right, at that constant value. So now we want to compute the distribution function corresponding to this random variable. Okay. So what do? You follow the definition. So the distribution function of x evaluated at any small x in the real line. So that's nothing but p compose x inverse of the interval, right? And therefore here in this case P compose X inverse is the Dirac mass, Dirac measure supported at the point C. And what does Dirac measure do? It checks whether the point C is in this interval or not. Now that means that if the point C is not in the interval minus infinity to x closed, if it is not there, you will assign the value 0. If the point is there in the interval, you will assign the value 1. So this is simply following the definition of the Dirac mass. But then you can rewrite this condition C belonging to these sets or not in terms of certain simple inequalities. What are these inequalities? C will not belong to this interval minus infinity to small x closed if the point small x is strictly less than small c, and it will be exactly equal to 1, that is the point C is exactly in the set if the small x is exceeding the value c or equal to c. Okay, and that's exactly the distribution function of the degenerate random variable taking the constant value c. Okay, so you get back your familiar values for the distribution functions. Okay, but this is through the law now. All these computations are going via the law. Alright, and as we shall see, many of the properties of the random variables or random vectors are getting captured by this law. Okay, so we are now going to study the properties of distribution functions corresponding to probability measures or corresponding to random variables or vectors, and we are going to see that all these properties for these random variables or vectors that you have already seen in your basic probability course are reappearing here, and that's all. I mean, you are just matching up with whatever you have seen earlier. Okay, but important distinction, so far we have not talked about discrete or continuous random variables, we are doing everything in general. So that's a very big advantage of using this measure theoretic approach. Alright, so again, so let's start with these notations. So in proposition 2 you are looking at a specific random variable and we are listing certain properties of the distribution function, the well known properties. So what is this? The first property says that the distribution function is non-decreasing. So how do you go about proving this? So what do you have to do? You have to evaluate it at 2 points, small x and small y. So choose small x to be less than small y, strictly less than small y, and then you evaluate the values and try to check whether the function values you can compare. Okay, so look at this difference of these two quantities. So you evaluate it at small y and subtract out the value at small x. But then put in the definition, it's P compose X inverse of this interval minus P compose X inverse of this interval. Now use the finite additivity of the probability measure P compose X inverse and write the interval minus infinity to y closed as minus infinity to x closed disjoint union with open x to closed y. Okay, and one of the terms will cancel off with this, and that will just leave you P compose X inverse of open x to closed y. Okay, now this interval, whatever it is a set, it's a Borel set on R, and its size under the probability measure P compose X inverse cannot be negative. So always the size is non-negative. This is simply following the basic definition that a measure associates non-negative values. Okay, so therefore you get that fx of y is greater or equals to fx of small x. Okay, and this property follows quite simply from the basic definition that P compose X inverse is a measure, probability measure, and in particular it's a measure. Okay, so therefore the size of these sets will be non-negative. Great. So let's try the next property, that fx is actually right continuous. So how do you go about proving this? So what do you have to do? You have to verify the right continuity at all the points on the real line. So fix any arbitrary point small x. You want to verify that it's right continuous. Now the way to check right continuity will be to approximate the point small x from the right side. So choose such a sequence after coming to the point x from the right. So it's basically, you can choose it as a decreasing sequence of real numbers decreasing to the point small x. But then if you look at such intervals minus infinity to xn closed, they decrease and decrease to the interval minus infinity to x closed. This is a simple observation. And then you use the fact that the probability measure P compose X inverse is continuous from above. So you can go through the probability measures of these approximating intervals and after you take the limit, you will get back the probability measure of this resultant interval, right? So that's continuity from above, and therefore what you end up having is the right limit at the point small x. So let's compute that. So the right limit at the point small x is nothing but the limit of these points xn. So again, all you are going to show is that no matter what sequence xn you choose from the right approximating the point small x, you get the same value, so it doesn't matter. So here this limit is now independent of the choice of the xn's. So let's do the computations, and you will immediately see that it's really independent of the choice of xn's. So now put in the definition, it's P compose X inverse of such sets as we mentioned, but then use the continuity from above, and that's nothing but P compose X inverse of this. So it's really independent of the choice of the sequence xn. And now this quantity, whatever it is, as per definition, it's nothing but the distribution function evaluated at the point small x. So therefore the right limit is matching with the function value, and therefore the function is right continuous at this arbitrary point small x. Okay, so since x is arbitrary, the point x is arbitrary, you get the right continuity at all the points. But now let's look at the left limit versions of this. Okay, and it will turn out that there are possibly certain differences. It need not be left continuous. So what happens here? So you again look at the distribution function of x, and you try to evaluate these left limits at each point on the real line. You will get the left limit, but the left limit is exactly the length of such an interval, open interval, minus infinity to open x, and which can be written as the probability of the event capital X strictly less than small x. So how do you show this? So to show this, we follow the similar procedure to the argument in right continuity. So what we did there was approximating it from the right. Here we will approximating it from the left. So now xn will be a sequence which will be coming from the left hand side of x increasing to x, right? So look at this. So now these intervals minus infinity to xn closed, they will increase and increase to the interval minus infinity to open x. So this is a very important distinction from the case of right continuity. So here you do not get the boundary point small x. So this intervals minus infinity to xn closed, the union of those, they will actually turn out to be minus infinity to open x. Okay, great. And then what happens? You look at the corresponding sizes, and here you apply continuity from below because the sets are now increasing. Okay, so then the left limit evaluated at the point small x is again the limit taken over such sequences, and as we will see, it will again be independent of the choice of the sequence. So you put in the definition. So it's nothing but the size of the set minus infinity to xn closed evaluated in terms of the probability measure, right? So this is the size of that. Great. But you use the continuity from below, it will exactly be the size of the limit set, right? So it's minus infinity to x open, and you rewrite it, it's exactly the probability of capital X strictly less than small x. So the left limit is probability capital X is strictly less than small x, and this is again expected from your usual understanding or usual results that you have seen in your basic probability theory. So now we computed the right limit, we computed the left limit. You can now talk about the discontinuities that can happen for such functions. Okay, so you have a right continuous non-decreasing function. You have shown that it's right continuous, it has left limits, but there might be some issues with the discontinuity at these points. Okay, so the claim is this, that the only discontinuities of fx, the distribution function of x, are jump discontinuities. Again you get back the familiar properties of the distribution function. And now we can also say something about the jump size. Again you get back the familiar property that the jump size at any point small x is exactly the probability of the event capital X equal to small x, which is nothing but now the size of the singleton set small x in terms of the probability measure P compose X inverse. So how do you prove this? So to talk about the discontinuities of this non-decreasing right continuous function, you just look at the left limits and the right limits. Since the left limits and the right limits exist for any arbitrary point, you do not get any other type of discontinuities. Only possible discontinuity is a jump discontinuity. Okay, so where the jump discontinuity simply means that the left limit and the right limit do not agree. So the jump discontinuity can occur only when the left limit and the right limit at a point do not agree. Okay, so let's try to see that. So if fx has a jump, that means that you get a difference of values here. So the left limit and the right limit might not match. So look at this difference now. So as per the calculations above, it's nothing but the size of this interval minus infinity to x closed, and then you are subtracting out the size of the interval minus infinity to x open. So this is again all the expressions that we have derived earlier. But then you again use the finite additivity of the measure p compose x inverse and write the interval minus infinity to x closed as the disjoint union of the open interval minus infinity to x open and the singleton set point small x. Okay, so therefore you will exactly end up with the size of the singleton set small x under the probability measure p compose x inverse, and that's nothing but the probability of the event capital X equal to small x. So whenever there is a mass situated at the value small x, whenever x takes the value small x with some appropriate probability, positive probability, then you get a jump. Okay, so that's exactly whatever you have seen in your basic probability theory. But then you can also consider limits at infinity and minus infinity. Again, this will follow from the basic properties of the probability measure p compose x inverse, and this will match with the properties expected from your basic probability theory. So what happens here? So look at the limit at infinity, right? So what is this? So you are looking at the limit of the distribution function values as the point small x goes to infinity. So put in the definition. So it's the size of the interval minus infinity to small x closed under the probability measure p compose x inverse, and you are letting small x go to infinity. But these intervals minus infinity to x closed increase to the whole real line. So remember, these sets are contained in the real line, and if you look at the union of these, if you go over sequences, you will exactly get back the whole real line. And you now use continuity from below here. Okay, so when you are taking limit at infinity, you use continuity from below, and hence what you end up with is the probability of the whole real line under the probability measure p compose x inverse, and that's exactly equal to 1. So you get back the limit at infinity to be 1. And now what is the limit at minus infinity? You have to look at the limit of the sizes of these sets minus infinity to x closed, but these sets are now decreasing. If you choose a sequence of x going to minus infinity, you will immediately be able to show that these sets decrease and decrease to the complete intersection, which is the empty set, and therefore the probability of that is exactly 0. Okay, so p compose x inverse, the size of the set empty set under the p compose x inverse is 0. Okay, so therefore the limit at minus infinity is 0. So we are going to call this limit at infinity as fx evaluated at infinity, and limit at minus infinity as fx evaluated at minus infinity. So remember, the original distribution function for this random variable x was defined on the real line, but we have just extended the values of the function to the points plus infinity and minus infinity, and therefore you can think of the distribution function fx as a function on the extended real line. So this we can use later on. Okay, so this fact we will be using later on. But now you can derive other familiar properties like the difference of the function values for any two points a less than b, a strictly less than b, is exactly this quantity. Again, you follow the definitions that for a, b, when they are finite, so when they are real numbers, you can put in the calculations once more, put in the definition p compose x inverse of the set a open a to close b. So this is simply calculating by the finite additivity of the probability measure p compose x inverse. So you first put in the definition of fx in terms of p compose x inverse, apply the finite additivity. So this was discussed in statement Roman 1. Okay, so you get back exactly this type of probability of events. Okay, but then let's see if we can interpret these results when a equals minus infinity. Now that we have talked about the function values at infinity and at minus infinity, we would like to make sense of this equality if it holds in the cases when a is minus infinity or b is plus infinity. Okay, so now the idea is this: the left hand side makes sense because you have defined it, and all you have to do is to take appropriate limits on the right hand side. Okay, so this part of the proof is left as an exercise. Please use the definitions of the function values at infinity and minus infinity as discussed above. Okay, so please try to see this, that these appropriate versions of this equality holds when a equals minus infinity and b equals infinity. Of course, you have to use your familiar interpretations of such intervals whenever you are dealing with the cases a equals minus infinity, b equals plus infinity. Okay, so please use the appropriate interpretations as given in the week 1 discussions. But then you can extend this idea that you have obtained for one single interval open A to closed B to finitely many such intervals. So if you choose such pairwise disjoint intervals, you can look at the size of the union. So this is a disjoint union, finite disjoint union of such sets, and look at the size of this under the probability measure P compose X inverse. So it's nothing but the P compose X inverse of the individual sizes, right? So it's a finite summation for using finite additivity. And now individually these sets have the size which is given by the difference of the function values. Okay, so for all these types of finite disjoint union of left open right closed intervals, you can get back the probability measure by the difference of the function values. Okay, so this is again a simple application of the finite additivity. But now let's observe this, that the construction or the definition of the distribution function as defined from the probability measure associated to the random variable or the random vector, this is leading us to a function of this following form. Okay, so here we are just continuing on to add the details as discussed in note 4 earlier. So I will just recall what we did in note 4. So in note 4 we said that given this collection of possible probability spaces and random variables on top of it, we have this collection, the first collection. So the second collection is the collection of all probability measures, and we make this association. We created this function that sends elements from the first collection to the elements in the second collection. So you get probability measures but just by looking at the laws of these random variables X on the domain side. But then for every probability measure now, you have now sent it to a non-decreasing right continuous function with the properties that the limit at infinity is 1 and limit at minus infinity is 0. Okay, so this is just extending the figure 1 that was mentioned in note 4. We have just added figure 2. We have associated a function, appropriate function with some nice properties with every probability measure on the real line. Okay, so here we have just stated the one-dimensional version of this. So we have taken things for the random variables, and therefore you get laws in terms of probability measures on the real line, and then corresponding to that you get distribution functions with these properties again defined on the real line. Okay, but later we'll talk about higher dimensional versions. But now importantly, as mentioned in note 4 earlier, we mentioned that we are going to construct a function going in the opposite direction of figure 1. We are also going to construct a function which goes in the opposite direction of figure 2. So what we are going to do is, to given functions of this type, non-decreasing right continuous with limits at plus infinity, minus infinity given as 1 and 0, given such functions we are going to construct probability measures on the real line. So that will basically make certain identification between collections of random variables, collections of probability measures, and collections of distribution functions. So we'll make all these connections, and that will be via certain functions which go in the opposite directions of figure 1 and figure 2. Okay, so we will see that, and this will actually allow us to construct probability measures on the real line from certain class of functions. So we will see that later. Okay, now we have discussed the properties of the distribution function for random variables. Okay, but then analogous properties can be proved for random vectors. Okay, so all you have to do is to follow the definition and get back your familiar properties. Okay, great. Just for simplicity, let's look at the two-dimensional case. So this is a two-dimensional random variable or random vector. So what you can check now, this I have left as exercises. What you can check now is that if you let x1 and x2, these points going to infinity simultaneously, so the limit at infinity, that limit for the distribution function defined on R2, right? So I am saying that this will be taking the value 1 at the limit. Okay, so you can define the function value, extend the function value at infinity comma infinity. Okay, so please try to check this. Follow the definition through the definition given by P compose X inverse. Here X is a two-dimensional random vector. Similarly, you can talk about limits by fixing one of the coordinates and letting the other one go down to minus infinity. Okay, So if you do that again by the similar calculations as done for the random variables case, the one dimensional case, you can again show that both these limits will be 0. Okay, so if you fix one coordinate, let the other go down to minus infinity, you will get the value 0. Okay, so again these properties simply follow from the continuity from below and above of the probability measure P compose X inverse. So please check this and try to write down these proofs. But then for the two-dimensional case, what is the version of the non-decreasing property? So here what you can do is that you start with two values, two real numbers x1 and x2, and again choose another two real numbers y1 and y2. So you are going to choose these points x1, x2 in the first coordinate and y1, y2 in the second coordinate. So look at this kind of a product of intervals. So this is a two-dimensional set. So the first coordinate lands up in open x1 to closed x2. Second coordinates land up in open y1 to closed y2. So now this is a nice set in the Borel sigma field on R2, and if you look at the size of that, will be non-negative. That is simply by the definition of a probability measure. But then what you can observe now is that P compose X inverse of this interval can be written in terms of the certain relations involving the distribution function. So what you do is that you rewrite you compute the function values, the distribution function values at these points. So start with x2, y2, subtract out these two quantities and add up this quantity. And what will happen is that since the probability of the product of intervals is non-negative, you get this inequality that this combination of the function values must also be non-negative. This is what we refer to as the non-decreasing property of the distribution function fx. So this is in the two-dimensional case. So you get back the non-decreasing property following the properties of the corresponding probability measure. The measure associated to these sets, the product of intervals like this, the rectangle sets, is non-negative. Okay. And question is, how do you prove such a relation? How do you go from probability of product of intervals to this thing? The hint is that you use the inclusion exclusion principle. So please try to work this out. Now again you have this familiar property of right continuity. So all you have to do, you have to let the limit for each of the coordinates. If you take the limits each coordinate simultaneously, you get back the actual function value. So again this will be using the property of the corresponding probability measure P compose X inverse. All you have to use is the property continuity from above. Alright. But then you can also work out the d-dimensional versions of this. So we have started with the one dimension. Just for simplicity, we have just given a brief outline or brief ideas about the two-dimensional case. But now we are saying that the analogous versions hold for the d-dimensional case also. So please try to work out the non-decreasing property, the right continuity and other properties. Okay. So please write it down. So this is for the d-dimensional case and that is left as exercises. Now a final comment is this, that as indicated in note 8. So what was note 8? So let's go back to that. So the note 8 was this connection between random variables to probability measures and to probability measures to the corresponding distribution function. So this was stated for the dimension 1 case. So we are now going to state certain things about the d-dimensional case. So there is a corresponding version for the d-dimensional case, for the random vectors case, right? So you actually have to start with random vectors on some probability space, go to the corresponding law, which is a probability measure on RD together with the Borel sigma field on RD, and then corresponding to that probability measure you get a distribution function. You get this connection starting with random vectors, go to the probability measure which is its law, and then go to the corresponding distribution function. So this connection, please try to write it down for the d-dimensional case. So in note 8 it's written for the one dimensional case. Please write down the d-dimensional version. We are going to continue the discussions about properties of the distribution function in the next lecture. Specifically, we are going to talk about the germs of distribution functions. Okay, so we stop here.